Check out our homework on page 665, number 4 to 11. Any issues with any of those questions? 4, 5, 6, 7, 8, 9, 10, 11. Glenna? 9, 10, 11. All right. I heard somebody else say number 11. Rachel? 7. Is this going to be one of those? Yes. We got 7, 9, 10, 11. Going once, going twice. Really? All right. Number 7. Why does a diverging convex mirror have a virtual focal point and not a real focal point? Who can answer that question for me, please, number 7? Why does a convex mirror or a diverging mirror, whatever you want to call it, have a virtual focal point? Tristan?
Because technically the rays are converged on the inside of the mirror, so they converge at a focal point that doesn't exist.
Kinda. Tristan said technically the rays would converge on the inside of the mirror, so they converge at a focal point that doesn't really exist. You're kind of half right. They're not converging at a focal point on the other side. Rather, the dotted lines are converging. The extensions of the rays are converging, which means nothing's really converging. Rather, what's the other word that's like converging, except without the con? They're diverging. Yeah, they're diverging away from that. So we call it a virtual focal point because there's no rays really converging there. The rays are virtually converging there, which is kind of what you said, Tristan. They're virtually converging there because it's dotted lines, and that's what you said, dotted lines that intersect, which are the extensions of the real rays. So the real rays are diverging. It's these imaginary lines or these virtual lines that are converging. So if we don't have anything really converging there, we can't call it a real focal point. It's a virtual focal point because rays only virtually converge there. Number 9, draw a ray diagram for a converging mirror and determine the image characteristics where the image is located at twice the focal length, 0.5 the focal length, and 3 times the focal length. These are exactly the ray diagrams that we drew on our templates, right? The first one, maybe we kind of mistook or misunderstood what they were really asking for in question 9 and 10. Let me just copy those over real quickly and draw a couple of them and show you exactly what they're asking for there, okay? So we want to draw a ray diagram where we have a converging mirror. Converging mirror is going to look like this. Here's my focal point. Here's twice the focal point. In the first case, we say that the object is at twice the focal point, twice the focal length, whatever that is. First ray is going to go parallel to the principal axis. And then it's going to go down through the focal point. Second ray is going to go down through the focal point, and then it's going to go parallel to the principal axis. And in the end, the image, I cheated a little bit, the image should be right below the object, but the most important thing is that you get the right characteristics here. The right characteristics are evident, I think, on this. First of all, size. Larger, smaller, same size. It's going to be same size, right? Same size. It's going to be inverted, and it's going to be real or virtual. Real because solid lines are intersecting. We could project it onto the screen if we want. Let's do it at 0.5 f. Once again, here's my focal length. Here's twice the focal length. Here's my object at 0.5 f. First ray, parallel to the principal axis, down through the focal point. Second ray is going to go up from the center of curvature, and it's going to reflect back down through the center of curvature. Let's extend them. Okay, it looks like that. Let's draw our image there. We know that that image is clearly larger. In this case, it's clearly right side up, and it's real or virtual. It's going to be virtual, yes. 3F. So now we're drawing a ray diagram where the object is way out beyond the focal point. Okay, the object is out here 3 times the focal length. First ray, parallel to the principal axis, down through the focal point. Second ray, down through the focal point, parallel to the principal axis. They converge right here, which means this image is going to be smaller, it's going to be inverted, and it's going to be real. We could project this one onto a screen. Number 10, the ray diagram for a diverging mirror and the image characteristics. Diverging mirror is like the quiz question that we had, right? And all of those ray diagrams on the diverging mirrors end up being effectively the same. Okay, first ray goes parallel to the principal axis. Let me erase something here so we've got some space. Doesn't matter where we put it. First ray goes parallel to the principal axis, and then it diverges away from the focal point. Second ray is going toward the focal point, and then it's going to reflect parallel to the principal axis. We're going to extend those. Reflected ray right here, the reflected ray right here, and we're going to find that our image is formed in all three of these cases, A, B, and C, looking something like this. Characteristics that are smaller, upright, and virtual. Smaller, upright, and virtual. Make sense? I don't think we need to go through all three of these because we're going to draw all three of them exactly the same way. The last question that we had to go over here was number 11. It said some flashlights and headlights. This is a good question, actually. Some flashlights and headlights use concave mirrors to help generate a light beam. If the light source is positioned at the focal point of the mirror, would all of the reflected rays travel outward parallel to the principal axis? Explain your answer and include a ray diagram. I went over this yesterday with one person. There's our headlight, our curved mirror, okay, the headlight. We've got a focal point right here, and let's say we've got the radius right here, or twice the focal point right there. Let's say that we have a whole bunch of beams of light coming in that are parallel to the principal axis. Where are they going to reflect? They're all going to reflect to the focal point, right? Well, what if I have a light at the focal point? Just a point source light, a little light at the focal point. Well, it's going to emit rays of light in all different directions, including in this direction, and this direction. Where's this ray of light going to go coming from the light source? Where's it going to bounce off the mirror? Parallel to the principal axis. Where's this ray of light going to go? Parallel to the principal axis. Where's this one going to go? Parallel to the principal axis. You can imagine all other rays that are parallel to the principal axis will converge at the focal point, and therefore all other rays coming from the focal point striking the mirror will bounce off parallel to the principal axis. That's why when you look in your headlights, it's aiming forward as opposed to just everywhere, right? They're shaped that way on purpose. You don't want to see over in the field beside you. You want to see in front of you. So we aim those headlights, we design those headlights so that it directs a beam directly in front of it. Okay, the discussion that I had with, I think it was Cole yesterday, right, about this, I asked him if he had satellite TV. Who has satellite TV here? Like ExpressView or whatever? Okay. Used to? Okay. More than half of you have satellite TV. You see a dish on the side of your house. That's not the satellite. The satellite obviously is the thing that orbits around the Earth. A geosynchronous satellite, we call it. It stays in the same position above the Earth all the time, and that's why the satellite receiver on the side of your house doesn't have to move. It's pointed in one direction, and it stays in that one direction because it's aimed at the satellite that's up in the sky in the same position above the Earth at all times. The further an object producing waves are, EMR waves, is away from the receiver, the more parallel the rays are. Let me draw a little picture of that. Here's my satellite receiver. Here's the focal point of the satellite receiver. Here's an object. Okay, rays coming from that object are going to go in every which direction, right? Let's create another object over here now, same size. Rays coming from this object are also going to go in every which direction. You can see, though, that these rays that actually strike the mirror are going to be closer to being parallel to each other, right? Because the rays that are further away from being parallel to each other are going to miss the mirror. When you're further away from the mirror, the less parallel they are, the less likely they are to actually strike the mirror. You can imagine if this object is way out here in space, then you can imagine there's a whole bunch of rays that are not parallel, but they're not going to hit the mirror or the satellite receiver. The ones that are effectively parallel to each other are going to hit the satellite receiver. So basically what we have here with this satellite receiver is a whole bunch of rays that are parallel to the principal axis, or at least effectively parallel to the principal axis. Where do they converge? At the focal point. Well, if you look at the satellite receiver on the side of the house, or of your house, or on the roof of your house, you're going to see that this satellite receiver has the dish. But it also has this thing sticking out from the dish with this metal thing right there. That metal thing is at the focal point. That's because the radio waves that are coming from this satellite in space are going to converge at that point. We want all of those radio waves to come together in the same spot. Anybody can do this. Anybody can take a satellite dish or even make a satellite dish and receive this signal. Anybody can. You don't have to pay for that. Anybody can do it. But unless you pay for it, you're going to get a scrambled signal. You're going to get a signal that you can't do anything with. You can't watch. There's a decoder that you hook up, basically a decoder that you hook up to it that you can use if you're paying for it. So everybody gets the signal. Everybody, at least that has a dish, gets the signal. But it's only the decoder that, it's only the people that are paying for the decoder that are actually going to be able to watch the TV. Does that make sense? How do they broadcast this? Say you're at the TV station. How do they get the signal up to the satellite to begin with? You know the answer to this question. It's much like question number 11 here. How do they get it up to the sky to begin with? No. They have a satellite dish, but it's not a satellite receiver. It's a satellite dish producer or emitter, or whatever you want to call it. Basically, it emits the signal and directs it up to the satellite in the sky. Where do you think it's going to emit the signal from? The focal point. It's going to send the signal in this direction, in this direction, in this direction, in this direction, and all of those rays are going to reflect parallel to the principal axis. And as long as they have that aimed at the satellite in the sky, then we're all good. Make sense? Now you know how satellite TV works. Now you know how to steal a satellite signal. Can't do anything with it, but you can take the signal. Got it? All right. I want to introduce our next topic here. We won't get very far with it, but it's long enough to give you an analogy to describe what this next topic means. Refraction, we're going to define as the bending of light. Well, I shouldn't say that. The bending of a wave. But specifically within this unit, of course, we're talking about light, or we're talking about EMR. Bending of a wave. Due to the change in speed. Let's create a little analogy here. Let's say we've got, and if you were in Physics 20 with me, you would have seen this analogy before when we talked briefly about refraction in Physics 20, although not nearly as much detail as we're going to in this unit. We've got a parking lot here. The bottom side of this parking lot is pavement. Over here on the edge or the outside of the parking lot, or beyond the edge of the parking lot, we've got a swamp. So we've got people parking in the bottom half of the screen, and then in the top half of the screen, we've got alligators, or just a swamp. Let's say, for whatever reason, we've got some soldiers marching in this parking lot. I don't know why exactly they're marching in this parking lot, but it doesn't matter. They're trying to deal with the alligator infestation. Yes, you're right. That's exactly it. Here's the soldiers. They're all in a line. This is such a huge problem, these alligators, that there's a news crew above in a helicopter that's reporting on this. Now, the people from above in this helicopter are looking at these soldiers, and they see them basically as a straight line, like a wavefront. Yeah, like the crest of a wave in a sense. Now these soldiers get their orders from the general, and they start marching forward. They start marching this way. They're all marching in strides, so soldier 1, 2, 3, they'll all beside each other in 10 seconds. Soldier 4, A's still beside the rest of them 10 seconds later. This guy, though, soldier 5, what happens to him when he goes into the swamp? Let's assume he doesn't get eaten by an alligator, okay? What happens to him when he goes into the swamp? He's going to slow down, so he's not going quite as fast. So now this guy's in the helicopter, that news crew, looking down, are going to see something like that. That wave front, or that line joining them, it's straight, but then it kind of bends there at the edge. A few seconds later, soldiers are still marching. Soldiers 1, 2, and 3 are still in the parking lot. Soldiers 4 is now in the swamp as well. Soldier 5 is still in the swamp. Join them together. This is what the news crew sees. A few seconds later, soldiers 1 and 2 are out of the swamp, but 3, 4, and 5 are now in the swamp. Here's what the news crew sees. Okay, news crew sees essentially a wave front going vertical until it hits the boundary between the pavement and the swamp, and then what happens? It changes direction. Why did it change direction? Because the speed changed. The speed changed because the medium changed. The process of refraction is just like that. When light or any kind of wave enters a new medium at an angle, it changes speed. And because of that change in speed, it's going to change direction as well. Does that make sense?
Yep.
All right. Have a good weekend, guys. We'll see everybody on Monday morning.